I'm still in the paper generation. I am not electronic. We will walk from NCAR, which we will carry people down to in cars. That's about several miles south of here. Over Green Mountain, which is one of the bumps on the ridge. Come outside and I'll point at it for you. And then we're arranging them so you can walk back down baseline to the dorm. I'd say it's about 7 or 8 miles total. We'll do a car shuttle up to NCAR. We will depart at 8:30 in the morning from the big parking lot to the west of Pittsburgh. I've drawn a map on a piece of paper back here. Drivers, please sign up so that I know we have drivers. We have a bunch of locals who are shuttling people back and forth. Hikers, please sign up so we have a head count. So I have a rough idea how many people are coming. This is not binding, right? You can sleep in if you want to, and we won't come looking for you. Let's see. In the Boulder Mountain Park, there is no snow. There is a very, very high probability of an afternoon thunderstorm. The weather on Sunday is supposed to be cool. That's why I'm starting at 8:30. I could start earlier, but we're all exhausted. Bring lunch. I will bring 2 liters of water. Bring rain gear. Okay. If you want to do something which is easier or harder, I'll put descriptions back there. See me. I can send you on some real killer hikes. Okay. If you think you're tough. Okay. On the other hand, if you're a nice person and you want to walk for a few hours along a flat trail and smell the flowers and things like that, no, I'm completely serious. You can do that too, but I would like to know about it sort of before we're driving people up there. And don't come up to me at 8:35 when I'm completely dry and say, I really don't want to go on the hike. I want to do something else. I will be very flighty. If you do it before, then I'll call. So I'll put stuff back here, sign up, and then we'll see what we have. Okay, take it away.
All right. Good. So last time we introduced radial quantization, so now I want to talk about something that makes it look a little less weird, which is CFT on a cylinder. So in general, when you have a conformal killing vector, it's often useful to change your conformal frame, so do a vial rescaling of the metric so that the conformal killing vector becomes a regular killing vector, an isometry. And the way to do that for dilatation, so the star of our show before was the dilatation generator. This is not an isometry of flat space, but it is a conformal isometry. And the way to make this into an isometry is to start with the metric on flat space. And let's write it in polar coordinates. So this is the metric on SD minus 1. And just pull out a factor of r squared. And then let's define r as e to the tau. So this is e to the 2 tau, d tau squared plus d omega d minus 1 squared. And this is bigger. Sure. So e to the 2 tau, d tau squared plus d omega d minus 1 squared, where we've defined r is e to the tau. And this is the metric on SD minus 1 cross r. So what we've done is taken flat space with all these circles and done a vial rescaling to turn this into the cylinder. The cylinder with time coordinate tau. Okay. Under this rescaling, the origin maps to negative infinity in time. So that's where the origin goes. And then the point at infinity in flat space maps to positive infinity in dilatation time. Now, under a Weyl rescaling, the correlators of a CFT transform very nicely. So if we start with the correlator in some metric G, then this is equal to the correlator in a new metric. So we'll have some stuff times the correlator in a new metric, which is a rescaling of G by some possibly position-dependent factor. And the only things that you get here are just contributions from the rescaling of each individual operator. Good. So if we have a correlation function in flat space, then we can get the correlation function in any space that's conformally equivalent to flat space. And there's actually a piece that I'm not writing here, which is that there can be a contribution from the conformal anomaly, the Weyl anomaly. But we're not really going to care about that very much. The Weyl anomaly piece doesn't depend on any of the actual operator insertions. So it will be useful enough for our purposes to just normalize the correlators by the expectation value of the unit operator. And then the Weyl anomaly just cancels. Okay? So the Weyl anomaly is definitely interesting. It's especially interesting when if you're doing a Weyl rescaling that depends on the positions of the points. But we're not doing that here, so it's just going to cancel out. We can just think about this as being our expectation value. So in the case of the cylinder, so this suggests that we should define, given some operator in flat space, we should define the cylinder version of the operator. So it's a function of tau and a position on the d-1 sphere. So n is just the unit vector. We should define it as e to the delta tau, O in flat space, evaluated at e to the tau, say, x equals e to the tau n. So correlators of these operators should look like CFT correlators on a cylinder. And this is a nice exercise to check this. So compute a two-point function of cylinder operators. And check that it's invariant under tau translations. Okay, so the flat space correlators are definitely not invariant under tau translations. They transform in some particular way when you rescale things. But you should magically find that if you use the flat space answer, so that's the two-point function of O flat, and you plug in O cylinder, you should magically find that it has the form of something that actually makes sense on a cylinder geometry. Okay, so that's one thing to check. Another thing to check is expand in large tau 2 minus tau 1. So what do we expect on the cylinder geometry? Well, so if we act at tau 2 with some operator O, then we started with the vacuum. We act with O, and we create states in the conformal multiplet of O. So here in between, on this spatial slice, we have states with dimension delta. That's the primary. And we also can create descendant states. And then we propagate up, and we annihilate those states with another O, and then we just have the vacuum again. So what this suggests is that when you expand in this large time difference, you should get terms that look like e to the minus tau times delta plus n. Okay? So that's another thing that you should check for the cylinder two-point function. Any questions? Yes?
So where did that first one come from?
This thing?
Yeah.
Good question. So the way that you generate a finite you can generate a finite Weyl transformation by exponentiating a bunch of infinitesimal Weyl transformations. An infinitesimal Weyl transformation is equivalent to bringing down a stress tensor, specifically a trace of the stress tensor. So if we have some expectation value in a metric g plus delta g, this is equal to an integral dx delta g mu nu of x with the insertion of t mu nu. So in the particular case of a Weyl transformation, delta g is proportional to g. So let's say that delta g is equal to omega of x times g. So then what we're inserting here is omega of x times a trace of the stress tensor. Okay. Now the trace of the stress tensor is 0 as an operator equation. So that means it can have contact terms when it coincides with operators that are present. And those contact terms, you can figure them out by, so we know that the dilatation operator surrounding an operator of x, this is I delta O of x. Okay? And the dilatation operator is some integral over a surface of x nu t mu nu. And if you use the divergence theorem to rewrite this as an integral over the interior of the ball, you'll find that that the trace of the stress tensor is what appears, and it has to have a contact term with O that's proportional to delta. Okay? So infinitesimal t mu mu's with O of x prime look like this. Delta times a delta function of x minus x prime. Okay? And you can see by exponentiating these pieces, you're going to get this. So the Weyl anomaly is a little bit more subtle. The Weyl anomaly has to do with contact terms that appear when you have multiple t mu nu insertions. So another thing that happens when you exponentiate is you'll eventually, at high enough orders, you have more than one t mu nu, and they can have interesting contact terms, and that's what leads to the Weyl anomaly piece. Other questions? So actually, this is kind of cool. This is a pretty non-trivial claim that this thing is actually a cylinder two-point function. So the claim is that if you take the Ising model, the the Ising lattice model, and you compute correlators in flat space at the critical point. And then you do this transformation. You get some answer. Now we take the same lattice model and we put it on a completely different geometry, the cylinder, put it at the critical point, compute correlators, and then the answers should agree. So it's a non-trivial property of a consequence of conformal invariance that this should happen. Okay, good. So it's a good idea to think about radial quantization in this picture because a bunch of properties become clear. So I was asked a few times about why this thing is the vacuum state in radial quantization. Because usually we think to prepare the vacuum you need an infinite amount of Euclidean time evolution. This is something that we've used a lot, but this looks very finite. Yes. Good. Yeah, that's a good point. Yes, this is true for primary operators. Otherwise, you have to be more careful about what the contact terms are. Great question. In fact, I'll put that on the board. And of course, you can recover the answer for descendants by taking derivatives of this formula. Other questions? Okay, so I was asked why this thing should be the vacuum. It doesn't look like it has an infinite amount of Euclidean time evolution going on. And the answer is that actually it does. It's an infinite amount of dilatation time. So this, in this picture, maps to doing the path integral from negative infinity in dilatation time up to some fixed time. Okay, so in this picture, it's just the usual preparation of the vacuum state. So there's another physical property that becomes clear thinking about this picture. And to talk about it, let's first have an interlude on reflection positivity. And why it's equal to unitarity. For many applications, we're interested actually in unitary quantum field theories in Lorentzian signature, and I've been talking about everything in Euclidean signature. So what is the translation between these two languages? So let's assume we have a unitary theory in Lorentzian signature, and we have an energy momentum generators, H and Pi. So in Lorentzian signature, we have operators at some time in position x, and this is given by e to the I ht minus I x dot p O of 0, 0, e to the minus I h t plus I x dot p. And now let's Wick rotate. And actually, I'll be interested for this discussion in Hermitian operators. So O of 0, 0 is O of 0, 0 dagger. So let's Wick rotate to Euclidean signature and see what kind of operator we have. So let's write T is equal to I guess I have a minus sign, I T Euclidean, minus I T Euclidean. And so then we get a Euclidean operator which is e to the h t Euclidean minus I x dot p 0, 0 e to the minus h t Euclidean plus I x dot p. So notice that if we have this, then the Lorentzian signature operators are also Hermitian. So O of Tx is O of Tx dagger. And this is true provided that H and P are Hermitian operators. So you just take this expression, take the Hermitian conjugate, and this thing turns exactly into this thing. But something different happens once we've rotated to Euclidean signature. Now if we try to evaluate the conjugate of this Euclidean operator, what do we get? Well, okay, we have to swap the orders of these things. H is Hermitian, P is Hermitian. So you can check, you convince yourself that the result is the same operator, but where we've flipped time, reflected time through 0. So, in other words, conjugation in Euclidean signature requires a reflection of time, of Euclidean time. So in particular, this means that in Euclidean signature, whether an operator is Hermitian or not depends on how you quantize the theory. So I've emphasized before that different quantizations of the theory really have different Hilbert spaces. And in each Hilbert space, each Hilbert space has its own notion of Hermitian conjugation. Okay, and these notions can look different. So, in particular, if you have some operator, and now let's say it has spin. Because of this reflection, the conjugate of this operator also involves a reflection of its spin indices. And so let's look at an example. Let's look at the Euclidean translation generators that we defined earlier. So these were P mu is minus I integral. And for now, let's just think about the usual kind of quantization where I've picked some spatial slices like this and some time direction like that. So the charges are an integral of T mu 0. Okay? And now applying this rule, you can see that P0 has a different property under complex conjugation from Pi. So P0 corresponds to having T00 here, which means that when we conjugate, we get two reflections in the time direction, which cancel out, and then we get a minus sign from the I up front. Okay, so P0 is anti-Hermitian. And Pi are Hermitian. Okay, so P0 is anti-Hermitian. We can write P0 is equal to I times some Hermitian operator H. And then we recover this formula up here. So this is all completely consistent. You can see that this funny type of conjugation property is consistent with having the usual Hermitian generators in Lorentzian signature, and vice versa. This looks a bit funny just because we quantize this way and we find that P0 is anti-Hermitian. What if we quantize this way and now we find that Px is anti-Hermitian? And that's fine, because the two different quantizations just involve completely different Hilbert spaces. They have completely different notions of complex conjugation, of Hermitian conjugation. It's totally okay. Everything is consistent. It's also good that P0 is anti-Hermitian, because that means that time translation, a time evolution, which before we were writing as e to the I to Euclidean P0, I guess I was calling it x0. This thing now, this is e to the minus x0h. So this thing causes suppression in Euclidean signature, which is what we expect. We expect correlations to die at longer and longer distances. Any questions?
Okay, if you pick your time direction here along this time direction, and by that I mean that which you use to evolve, be along the space time direction, yeah, that below. So that's presumably if you choose the wrong quantization.
No. So in this is a good question, and it's a tricky point. So in Euclidean signature, if I quantize this way, then the Hamiltonian is bounded from below and things die off. If I quantize this way, I have a new Hamiltonian in a different Hilbert space, and it's also bounded from below. So it's tricky. In the spectrum of Px in this quantization is different from the spectrum of Px in this quantization. The spectrum of Px in this quantization is, that just gives you like Fourier transforms, like momenta, that can be positive or negative real values.
The mistake I was making was take the spectrum of Px in this quantization and apply it to it.
Exactly. Yeah. They're just completely different operators, because they act on different Hilbert spaces. Oh, good. Yeah, thank you. Sorry. So R is the R mu nu is just minus 1, 1, 1, 1, or okay. So it's a reflection in the time direction.
Quantization have like a semi-classical limit? Like, does it make sense?
I'm not sure I understand the contradiction. Is the Cauchy problem well defined? When we're talking about quantizing with that direction being time, it makes sense in Euclidean signature. Okay, so in Euclidean signature, sort of all the directions look the same. So you wouldn't want to Wick rotate to Lorentzian signature and then quantize on time-like slices. Or maybe you would, but I haven't thought very much about what would happen in that case. It would be an interesting thing to try to understand. Okay, good question. Others? Okay, and you guys are used to this kind of this notion of time being different from the time generator being different from the space generator. I mean, the energy in Lorentzian signature is also bounded from below, but the momentum is not. So they just look completely different, and you can ask, how is that consistent with the rotational invariance of the Euclidean theory? And this is the answer. Okay, so good. So suppose we have some state psi that we create with a bunch of Euclidean operators acting on the vacuum. So the norm of this thing is then, okay, so I reverse the order of these guys, and I flip the times. And in a sensible theory, norms of states should be positive or non-negative. And this gives a condition called reflection positivity. Okay, so reflection positivity will be true in any theory where you start with a Lorentzian unitary theory. You continue to Euclidean signature, and then think about the correlators in Euclidean signature. They'll have this property because the states don't care about the what kinds of whether you're acting with Euclidean or Lorentzian operators. They don't care. The states always have positive norm. So the cartoon for this is that whenever you have some reflection symmetric configuration of operators, then this has to be bigger than or equal to 0. Okay, so great. So I guess I've shown you how if you start with a unitary theory in Lorentzian signature, then you get a reflection positive theory in Euclidean signature. And it turns out vice versa is also true. If you start with a reflection positive theory in Euclidean signature and you analytically continue it to Lorentzian signature, you get something unitary. And this is an interesting fact because sometimes if you have an explicit microscopic description of a theory, it's easy to check reflection positivity. An example is the Ising lattice model. That's always the example. So you can check for yourself that if you have some lattice like this and you insert some operator, let's say you insert the spin operator here and the spin operator at some reflection symmetric configuration, then you can check that the expectation value of these two spins can be written as a sum of squares. The idea is just to define a state by summing over all these spins, and then define another state by summing over all these spins, and show that this thing can be written as the norm of those states. So just check for yourself. Write out the sum over spins weighted by Boltzmann factors of this configuration, and check that you can write it as a sum of squares. And so it follows that in the continuum limit, this gives a reflection positive theory. So in particular, the Ising lattice model in the continuum limit gives a theory that we can think of as the Wick rotation of a unitary theory in Lorentzian signature. And sometimes it's interesting to think about this unitary Lorentzian version of the Ising model, and in fact it shows up in actual physical systems. So there are two ways that you can think about this theory. You can think about it as a classical statistical system that's reflection positive, or you can think about it as the Wick rotation of a quantum system that's unitary. Yes.
For this, you would have to have a reflection symmetric lattice, right?
Yes. Good. So to make sense of this explicit computation, you really need your lattice to have reflection symmetry. if you have a non-reflection symmetric lattice, then what can happen is reflection positivity can emerge in the continuum limit. So one thing that emerges in the continuum limit is continuous translation symmetry, and also continuous rotation symmetry, which is a little less obvious. So reflection positivity can also be a little bit harder to check. In general, different things are easier or harder to check depending on what microscopic description you use for the theory. But critical universality tells us, or we expect, that these different microscopic descriptions become the same conformal theory, and therefore you can conclude many things about the conformal theory by thinking about different microscopic realizations. Okay. All right, so that's reflection positivity. Now let's look at reflection positivity on the cylinder. So now we have a time direction, and we can define a notion of conjugation that takes an operator at some time tau to the same operator at minus tau. And this is a perfectly good notion of conjugation in the Euclidean theory. And in particular, we should have reflection positivity and all the nice things that we want. And in flat space, this becomes something interesting. So you can check for yourself using the dictionary between the flat space and the cylinder that this says that O flat of e to the tau n dagger is e to the minus 2 delta tau O flat of e to the minus tau n. And just to write it again, O flat of x dagger is x to the minus 2 delta O flat of x over x squared. And this is an inversion. Which makes sense. The time flip on the cylinder swaps negative infinity and positive infinity, so it swaps the origin and infinity in flat space. And that's what our inversion transformation was. So this is conjugation in radial quantization. And just to belabor the point, if you were thinking in a different kind of quantization, like the usual quantization, you would just have a completely different formula for what the Hermitian conjugate of the operator would be. Okay, so inversion is the thing that does the time reflection for us. And this means that the conjugates of our conformal generators in radial quantization are given by conjugating their killing vectors with an inversion. So check for yourself that this means that mu nu is Hermitian, which makes sense because if you rotate and invert, it's the same as inverting and rotating the same way. Inversion does nothing. More interestingly, D is anti-Hermitian because inversion switches the direction of dilatation time. And P mu gets conjugated to K mu. P mu is a translation around the origin. K mu is a translation around infinity. So we have these funny conjugation properties of the conformal generators in radial quantization. This one in particular, note that this says that D is anti-Hermitian, so its eigenvalues are I times some real number, which is something that I've been claiming. I claimed a bunch of times on physical grounds, but here you can see why it's true. It's true in a reflection positive theory. Okay, so now we can have a lot of fun. We can do stuff like computing correlators just using the algebra. And this is a nice computation just to give you a feel for how these sorts of things work. So let's consider a two-point function of operators. We'll take them to be scalars for simplicity. So, and I'll assume that that y is farther from the origin than x, so that in radial quantization this becomes O of y, O of x, sandwiched between the vacuum. Now, what is this thing? Well, we can write it as the conjugate of something. Okay, so here I'm just using this formula for conjugation backwards. Okay, but what is this? Well, O at this inverted position is given by translating with our translation generators. Let me just write this as O, the state O. And now we can use our rules for complex conjugating the conformal generators, which say that this is equal to the conjugate state e to the plus I k dot y over y squared. All right, so now we have an expression for our two-point function, y to the minus 2 delta O e to the I k dot y over y squared e to the minus I p dot x O. And we can evaluate this using the conformal algebra. So as a just for simplicity, let's expand this thing to first order. So we have 1 plus a term with k plus a term with p plus a term that I'll write more explicitly with both of them, y mu over y squared, x nu, k mu, p nu, plus dot dot dot. So what happens to this term? Right, right. So O is primary, so this thing just kills O. What about this term? Same. Why the same? Right, because it goes that way. Okay, good. All right, so the interesting term is the first one and the last one. So for this one, you guys, I'm sure, can see how this is going to go. We have to evaluate this. But O is primary, so we can replace this product with a commutator. And now use the conformal algebra to replace this commutator with minus 2I d delta mu nu minus m mu nu. We're considering scalars for simplicity, so this is just equal to 2 delta. All right, so the result is that we get y to the minus 2 delta, the norm of this state, times 1 plus 2 delta x dot y over y squared plus dot dot dot. And so you should check that this agrees with the usual formula. When we expand it in small x over y. And so now you can imagine doing the same thing for all the terms, and you should magically find that if you do this exercise a billion times, it gets infinitely harder and harder, and resum everything, you should just get the two-point function. So this is another way of understanding why the two-point function is fixed by conformal invariance. Questions? Oh, good. So the commutator is kp minus pk. But the pk term is 0, because k acts on O to give 0. Other questions? So if you really, really like that computation, you can do the same thing for a three-point function and show why it is also fixed by the conformal algebra. But probably a simpler exercise that you guys should also try. So we can consider, let's say, different operators and look at the dilatation generator or the rotation generator sandwiched between them. And in this case, let's allow the operators to be to have spin. Okay. So show that by evaluating these correlators in two different ways, acting first to the right and then to the left, you should be able to derive that delta 1 equals delta 2 derive that O1, O2 is non-zero if delta 1 equals delta 2, can be non-zero if delta 1 equals delta 2. Actually, maybe a better way to say it is O1, O2 is 0 if delta 1 and delta 2 are not equal. Okay, so this was something we derived earlier, but here you can show it using the algebra. And using this, you can show that the same thing, if the spins are different, then this has to vanish. And if you have identical operators, then this has to be proportional to the identity matrix for irreducible representations. Okay, so those are just some quick things you can check. Good. Okay, so the other thing we can get a lot of mileage out of is reflection positivity itself. And this leads to some constraints called unitarity bounds because reflection positivity and unitarity are the same thing. So let's think about an operator with spin. And I'll define its conjugate state with a lowered index. This is just a convention. So the reason for the lowered index is because complex conjugation will swap dual representations of SOD. This is totally unimportant. You can ignore the raising and lowering of these indices. Okay, so good. So reflection positivity says that norms of states have to be positive. So one thing we should demand is that the norm of this thing be positive, and so that means that this coefficient here is some positive number. All right, but we should also have that norms of descendant states are positive. So in particular, you can take a look at the first descendant of this guy. And take its norm. We can think of this as a matrix of norms for all the possible states. And reflection positivity says that this matrix, where we think of it as being indexed by nu b and mu a, has to be positive semi-definite. Okay, so you can evaluate this using the conformal algebra, and you should find that it's equal to 2 delta, delta mu nu, delta AB, plus 2I S mu nu, AB, where remember these were the finite dimension, these were the SOD generators in the finite dimensional representation associated to O. And the claim is that this thing has to be a positive semi-definite matrix. So that's what this funny greater than or equal to sign says, which in particular means that delta has to be larger than the largest eigenvalue of minus this. So delta is bigger than or equal to max eigenvalue of minus 2I S mu nu AB, where you should think of, again, you should think of this thing as being a matrix acting on the tensor product of the vector representation with the representation associated to O. And I'm going to skip the calculation of what this is, unless people want me to do it, and just write what the answer is. You can already see in the case of scalars, this gives delta is bigger than or equal to 0. Okay, so we've derived the thing that I claimed earlier, that the dimensions should be bounded from below by 0. Before I was demanding it from cluster decomposition, but here we just derive it from reflection positivity. So in general, the answer is that delta is bigger than or equal to 0 if L equals 0, and L plus D minus 2 if L is bigger than 0. Okay, so that was just from considering this matrix of norms. But you could also look at higher descendant states, and the interesting one, which is left as an exercise, is to look at p squared O and show that demanding that its norm be positive implies that delta is bigger than or equal to d minus 2 over 2. Or delta equals 0. It's also allowed. Okay, so the summary is that delta is equal to 0, or delta is bigger than or equal to d minus 2 over 2 for L equals 0, L plus d minus 2 for L bigger than 0. And we got this just by checking a few descendant states. In general, you have to check positivity of all the descendant states. But it turns out that positivity of all the descendant states will follow from these conditions. So you get no new conditions. Yes?
So delta equals 0 is the identity operator. Presumably something horrible goes wrong if you try to have more than one set state in your theory.
More than one identity operator.
More than one delta equals 0.
Well, okay, so the delta equals 0 states you will be able to show using the conformal algebra that their correlation functions are completely fixed to agree with the correlation functions of the identity operator. So it's not yeah. So actually, I think probably what you could have is super selection sectors, where you just have two completely decoupled CFTs, and you think about one state as being the... Actually, no, I don't think you can. I don't think you can. The ground state of the whole theory will be just the tensor product of the ground states of the two. Yeah, I think it just doesn't make sense to talk about two operators because their correlators are all exactly equivalent. Yes? Oh yeah, that absolutely makes sense. Sure. Yes. Mm-hmm. Yeah, you can. Yeah, I'm just claiming it here without proof, but it turns out to be true. If you have more structure in your theory, you can get more information. So, for example, in 2 dimensions, the algebra we've been talking about is a subalgebra of the full symmetry algebra of the theory. And then by considering the full symmetry algebra, you can derive even more constraints. Another example is in a superconformal theory. The conformal algebra we've been talking about is a subalgebra of the superconformal algebra. And by considering superconformal descendants, you can derive more constraints. Yes? Pardon? Yes, there are similar unitarity bounds. I'm not sure if I don't think they're derived in exactly this way, because you don't have this inversion property to use. Although I'm not completely certain about that. But one way to derive unitarity bounds in scale invariant theories is to consider, say, 2-point functions of operators in flat space, and simply demand that they have a good Callan-Lehman spectral decomposition. And so that will give you some kind of constraint. I think you get something like delta is greater than or equal to 0 or something in those theories, but I'm not totally certain. Other questions? No, the correlation functions don't have to be the same. So that claim that I made about delta equals 0 operators all having the same correlation functions is something very special to delta equals 0 operators. Basically, the Ward identities for delta equals 0 operators will be much, much stronger than the Ward identities for all other operators. So yeah, in general, your theory can have it should have a unique identity operator, a unique unit operator, and if it's not two decoupled theories, it should have a unique stress tensor. But other than that, you can have as many operators as you want. They can coincide in dimension and spin and so on. And their correlators will be different. The correlators are determined by OPE coefficients, which we'll define in a moment. Yes?
So because it's generally believed
it's true. It's certainly true in 2 and 4 dimensions, and in 3 dimensions, it's probably true for most theories outside of pathological cases. But yes, let's say that it's true. That's right. Yeah, I mean, if your scale invariant theory is also conformal, then you can just apply these bounds. Yes. Mm-hmm. S dagger S equals 1. That's sort of like that's basically just saying that time evolution is unitary, is given by some unitary operator. So that's equivalent to this statement about how the Lorentzian generators are Hermitian, so that when you exponentiate them, you get unitary operators. So we're assuming that. I guess unitarity has 2 pieces. One of them is that symmetries act with unitary operators on the Hilbert space, and the other is that norms with states should be positive. Yeah. Good question. Yeah, exactly. So the question was, what about a gauge field which has scaling dimension 1? And the answer is that a gauge field is not a local operator. It's because it's not gauge invariant. That's right. Yeah, I mean that's a good point also. Yeah, I mean it. Well, the operator transforms simply under Lorentz transformations.
No, not really. I mean, it's not shit. I mean, it comes from part of it. But it comes from it. Part of it. So you can write down Lorentz transformation so that of lambda in the universe of lambda is the correct piece, right? The lambda mu
Right.
mu, and then there's a derivative piece that looks like a gauge transformation, but it really comes just from the
Right.
Lorentz transformation.
Good. So you're using the expression for the gauge field in terms of the particles that you know it describes. Yes, that's true. Good. So yeah, we're always talking about physical observables, which means gauge invariant operators. Was there another question? I thought there was. Okay. Good. So what happens? What happens if these bounds are saturated? So this is true. So the bounds are coming from demanding that certain descendants have positive norm. So that means that when the bounds are saturated, there's some descendant whose norm is going to 0. So there's some null descendant So as an example, when this bound is saturated for a scalar operator, it means that this state is actually 0. So for a scalar, delta is d minus 2 over 2 implies that p squared O equals 0. And in operator language, this says that del squared O of x is 0. And so this means that the scalar is free. It satisfies the Klein-Gordon equation, and it satisfies the Klein-Gordon equation inside any correlation function. So its correlators will be those of a free scalar, and it just decouples from the rest of the CFT and is completely uninteresting. Well, if you're interested in free scalars, it's interesting. Okay, so that's this first bound. Right, if this one is saturated, then that's the unit operator. And then the other interesting one is this one. And it turns out that the null descendant in that case, so spin L delta equals L plus d minus 2, implies that the following descendant is null. So this is P acting on O, where we contract the index of P with the index of O. And the way to get this is to dig into the computation that I skipped of the maximum eigenvalue of that matrix. You'll find that this thing has to have norm 0 when this is true. And in operator language, this says that d mu O mu, mu2 through mu L of x is 0. And this is a conserved current. Yes?
Can I also use the formula for fermionic operators, which is half integer?
Yeah, absolutely. So there you'd have to redo this computation, and then you would get some other bound there. But that you can absolutely do.
Not just this one.
Yeah, it's not just this formula. Yeah, so that's a thank you for asking that. So in general, you can have operators in any representation of SOD. So in 3 dimensions, fermionic representations and spin L representations are all there is, because the rotation group is SO3. But in higher dimensions, you can have all sorts of interesting things, and they'll have their own interesting unitarity bounds. So let me just mention 2 important examples of conserved currents. One of them is T mu nu, the stress tensor. It has spin 2, and if it's conserved, it must have dimension 2 plus d minus 2. Okay, so this is an if and only if. The statement that it's conserved is the statement that it has a null descendant, and this implies that the unitarity bound must be saturated in this case. So this is L equals 2, delta equals D. And another example is a global symmetry current, which has L equals 1, delta is D minus 1.
But the intermittent tensor is not a primary operator.
It is. So no, it is a primary operator with respect to the global conformal group. If you have the full Virasoro algebra, you can redefine what you mean by primary. So usually primary means the operator with lowest dimension in the entire multiplet. So when you have a larger algebra, you have a bigger multiplet. You can go farther down in dimension.
That's a 2D thing.
It's a 2D thing. That's right, yeah. So in 2D, the language would be that the stress tensor is a quasi-primary. And actually, yeah, so this is true generically when you have a larger algebra than the conformal algebra. So for example, in supersymmetric theories, the stress tensor is not a superprimary. It's a superdescendant of some other primary. But it's always a primary under the global conformal group. Yes?
Can you have a central charge in dimensions other than 2?
Can you have a central charge in dimensions other than 2? You don't have extensions of the conformal algebra that contain a central element. There are things that people call central charges, but they're not really central charges.
So the 2U never gets that extra C term.
That's right, yeah. Yeah, the extra term in 2 dimensions also vanishes for global conformal transformations. Yes?
Does it ever happen in higher dimensions where you have non-physical combinations?
Good. So the question was, what if you have some more complicated null descendant? P1, P2, P3, P4, O equals 0, which would imply some fourth order differential equation. In higher dimensions, in a unitary theory, you cannot have those null states without having one of these simpler null states. And that's equivalent to the fact that there are no new unitarity bounds from considering higher descendants. In a non-unitary theory, this is no longer true. And then you can have a state such that O is non-zero, P squared O is non-zero, but P to the 9th O is 0. So you can ask, what are the correlation functions of these states? And I believe this is a research problem that you should work on. Other questions?
Why would I ever care about non-unitary?
Oh, well, yeah, that's a good question. So people haven't really cared so much about them, which is why that's still a research problem. But non-unitary theories can show up in condensed matter systems, certainly. If you have a quantum mechanical system, then it will be unitary because quantum mechanics. But if your theory is intrinsically Euclidean, then reflection positivity is something that it may or may not be true. It's true for the Ising model by that exercise I told you to check with the sum of squares, but you can write down other statistical theories that just aren't reflection positive. And you can also have actual statistical physical systems that aren't reflection positive. Good. One can also have higher spin conserved currents. But these are generally believed to be absent in interacting CFTs. So higher spin currents are present in free theories. The simplest example is for a free boson, you can define a primary operator, which is essentially phi with a bunch of derivatives sandwiched between them. And this is a higher spin conserved current, and that's related to the fact that free theories have an infinite number of symmetries. But in an interacting theory, you don't expect to have these, and there's a proof, certainly for 3D CFTs, and is there a proof in 4D CFTs? Great. Okay. It's being worked on. Probably. Sorry to put you on the spot, but okay. Yes, please, everyone discuss. Great. The general reasoning is just that higher spin currents are give very powerful constraints on the correlation functions, and the hope would be that if you work out all the consequences of these constraints, you can just derive that the correlators are those of a free theory. Oh, good. Yeah, thank you. So in 2D, you absolutely have higher spin currents. So the correct analog here is we're asking about quasi-primary states because we're just talking about the global conformal group. You can look at a quasi-primary that is a Virasoro descendant of the identity. It will be a holomorphic operator and therefore conserved. So that's the simplest example. You can also have more non-trivial things where you actually have a Virasoro primary that is higher spin and holomorphic. Those lead to interesting things like W algebras and so on. Yes?
What's the status of the trace of the numerical tensor in CFT?
The status of the trace.
Yeah.
Uh-huh. Mm-hmm. Yeah, I mean, from the point of view of a CFT, it's just the zero operator because the CFT can only tell you about correlators at separated points. Correlators at coincident points depend on contact terms. Sometimes those contact terms are fixed by symmetries. So, for example, that's the case with the word identity of the stress tensor. And it's also the case with the word identity of the trace of the stress tensor with some other primary. But sometimes the contact terms are not fixed by symmetries, and then we expect that they're dependent on the UV regularization of the theory. Okay, I was gonna give an argument about why the only states in a unitary CFT are linear combinations of primaries and descendants. I think I want to get on to more interesting things, so I'll just sketch it really quickly. The idea is that we now have an inner product that respects the conformal symmetry. So you can use this inner product to project states onto different conformal multiplets. Basically, you can show that if you have some state and you consider and you project it onto all the conformal multiplets with dimension less than or equal to that state, you can show that the result has to be 0. To get this to work, I had to make one physical assumption, which is that the partition function of the theory on SD-1 cross S1 is finite. I'd be happy to tell you about that after the lecture, but I want to get on to something more interesting, which actually uses that claim, so that's why I wanted to mention it. Yeah.
Were we going to go later?
Yeah. We're going to start a new topic.
Oh.
Stop and start the step.
Okay.
It's a new topic.
It's a new topic, yeah.
Yeah, then I think it would be better to stop here.
Yes. The claim is that all states are linear combinations of primaries and descendants. Yes. Good. So should I do the argument? The idea is so let's assume that the partition function of the theory on SD-1 cross S1 with some temperature beta is finite. So this is the trace of e to the I beta d, and this is less than infinity. Okay, so the first thing that this implies is that this operator, so in a unitary theory, this operator is Hermitian, and this assumption implies that it's trace class, which by the spectral theorem means that this operator is diagonalizable. And so hence D is diagonalizable with eigenvalues of this form. So that's a technical thing. We're allowed to diagonalize D in a unitary theory. So now let's consider some state O. And let's subtract from O the projection of O onto the conformal multiplet of all primary states. And for simplicity, and let's say, so P runs over primaries with dimension less than or equal to delta O. Okay? So using our inner product, we can define this projector, and then we subtract this off, and let's call this O prime. Okay? So now suppose O prime is non-zero. That means that by acting with K, we can eventually get down to a primary. Right? If we didn't get down to a primary, then we'd have an infinite number of states of more and more negative dimension, and that would contradict the finiteness of this. Okay, so by acting on O prime with k's, we get down to a primary. But we were supposed to have subtracted off the projection onto all primaries with dimension less than or equal to O. So that means O prime must equal 0. And this is in practice what you do. If someone hands you an operator in a CFT, you start subtracting off the components of that operator that are descendants of primaries with dimension less than it, and eventually you just get 0. Okay, so let's stop there and.
CFT is logarithmic. You cannot diagonalize D.
Yeah, that's right. So this is the thing that fails.
This is infinite in that case.
Yeah, I think so. Well, not necessarily. Not necessarily. Let's see. In a logarithmic CFT, what you don't have is unitarity necessarily. So you don't have that D is I times a Hermitian operator. So you need those two assumptions.
But if D is the mission, I can't diagonalize it. This is not always.
Just being Hermitian is not quite enough technically. I think physically, yeah. I mean, the theorem is that a compact Hermitian operator has a spectral decomposition, where compact is I mean, it's a technical condition on operators on Hilbert spaces, and this is definitely compact. Any operator that has a trace is compact.
Yeah, but if D were not compact, this exponential would be compact and it would be acknowledged.
That's right. If
Then you could not imply
if D
compact
is if D is anti-Hermitian. So that's the thing. In logarithmic CFTs, D just simply isn't her.
But you are saying that so if D were Hermitian but not compact, still I could be acknowledged. Always.
Yeah. That's right. I don't need D to be compact. I need the exponential to be compact. I need any function of D to be compact, and then you can get that D is diagonalizable.
But the exponential is nice because it makes it compact.
Yes.
But then I could not infer from there that D is diagonalizable. So I start with some D, which is Hermitian, non-compact, and non-diagonalizable. I don't know if those exist, but we are counting it. Now I exponentiate.
D will never be compact. So compact is basically the statement
No,
that.
okay, I understand.
Okay.
So, but suppose it's not diagonalized.
Okay.
It's Hermitian. It says that things will exist, right? Hermitian, non-compact, and non-diagonalized.
Yeah, those can exist.
Okay, so now I exponentiate it, and it is diagonalized. then I don't understand the implication because my assumption is not.
You're running circles around me.
So I start with D, which is not diagonalized.
Yes.
That's it. Then I exponentiate. Now it is the exponential is diagonalized.
Yes.
So how did you find the next implication sign that?
Well, now you get a contradiction. It turns out D was diagonalizable. So therefore, the assumption that D is not diagonalizable and Hermitian, and that this is finite.
No, but I think it's not. It just means that you cannot infer from an exponential to diagonalizable that the can diagonalize.
No. I think that's fine.
So then all addition operators can be diagonalized, which was my first.
No. You need that. You need that the exponential is compact. The exponential is not always compact.
I thought that putting that I there was sure that
Well, it depends on how the spectrum behaves.
if the spectrum is real, then that's going.
Yes, but now you're taking the trace. So the identity operator is not compact. Compact basically means that it squishes things more and more as you go to more and more eigenvectors. But maybe we should talk about this offline.
Sorry. So that was discussion. I was under the impression that D was on Hermitian logarithmic.
Yes, that's correct.
Okay, so then we would expect that.
Yes, that's absolutely right. Yeah. Yes. That's a great question. I don't really I don't know very much about null quantization and how it behaves. Okay, good.